So today we're going to be talking about relational databases and graph databases. This will be an introduction to graphs, graph databases, and Near4J from the perspective of the relational developer, someone familiar with relational databases. So as Corey said, my name's Will. I work on the developer relations team at Near4J. Specifically, I mostly work on some of our open source integration projects. So I write code to help integrate Near4J with other databases, other frameworks, then also spend a lot of time working with users and customers to make sure that they're successful with Near4J. So I love talking to users and customers. Feel free to ping me on either email or Twitter that are on the screen there if you have any questions after the presentation. So here's the rough outline of our agenda for today. We'll be talking about some use cases that make sense for graphs. We'll compare some of the issues that you may run into in a relational database with how that works in a graph database. We'll look at, from a technical perspective, how we build a Near4J application, including looking at the query language, look at some of the language drivers. Then we'll go through an example of converting a relational database to a graph database, mostly with the data modeling. We'll see how we would import that into Near4J, and then we'll have some hands-on queries to answer some interesting questions of that model that we've imported. So with that, let's go ahead and get started. And we'll get started by talking about data, and specifically the traditional approach towards data. So traditionally, when we've been working with data and applications, we treat data as these discrete elements in a system of record. So something happens, we make a sale, we record a transaction, we treat that as a discrete data point. We cram all of these into a table and use a relational database to store that data. So systems of record is sort of the traditional approach towards data. And we use this, the same approach across all functions in our organization, from HR tooling to supply chain, logistics, customer support, everywhere. However, there's been a huge change in the last decade or so towards a system of engagement. So rather than systems of record, users are engaging with devices. Users are engaging with other users. So think of social networks, think of users engaging with different devices, and then also devices engaging with different devices. Think of the Internet of Things. And so really with the shift towards systems of engagement, we're seeing this huge growth in data volume. And it's important to realize that we're only here at this point in this huge exponential growth in data volume. So we really have big changes coming. So it's really important that we make sure that the technology that we use to represent and work with this data are able to handle this huge explosion in data volume that we have. So if we compare systems of record from the relational database model to the NoSQL world, which has been the response to this initial growth in data volume, what we see in systems of record are more structured data models with pre-computed things. So let's take recommendations, for example. We may need to batch compute product recommendations in a system of record because we simply can't do those in real time. Whereas in the NoSQL world, we expect real-time queries. These things are on the hot path for web applications. So again, systems of record are very, very structured. Think of tables. Whereas systems of engagement, instead we need better understanding of the data in the context of the data. And if we look at the diagram here, well, this data is modeled as a graph. We haven't talked about graphs much yet, so let's answer this question of what is a graph. Well, when we're talking about a graph, we're not talking about charts, things like bar charts and pie charts. Instead, we're talking about a data structure. And this data structure consists of nodes. These are the entities or the objects in our graph, and relationships that connect the nodes. So really, a graph is just connected data. And what kind of data are we talking about here? What kind of data can we store as a graph? What kind of data is connected data? Well, there are lots of different types of connected data. We can think of roads that have traffic, that have some traffic lights. We can think of rooms in a hotel. Rooms have some availability with a calendar, schedule associated with them. And really what we're interested in is creating competitive advantage from how we use this data. And that's where graph databases and Near4J come in. So throughout this webinar, we'll see how storing our data and querying it as a graph allows us to create competitive advantage to answer interesting and business critical questions of our data in real time. So what are the benefits of a graph database that allow us to create this competitive advantage? Well, the first is intuitiveness, and this really has to do with the data model that we're talking about. So in an organization, usually when we start to map out some problem, we'll go to a whiteboard and we'll start drawing a diagram that looks like this. We start talking about the organization, departments in the organization, and so on. We end up drawing a graph on the whiteboard because this is how we think about our data. And the key thing here is that graph that we drew on the whiteboard, that is both our the way that we think about the data, and it's also our physical data model when we go to implement that in our application. So we don't have this impedance mismatch in our application from how we're modeling the data versus how we're thinking about the data. So this is a huge advantage, and this is the intuitiveness of the graph data model. The next advantage is speed, and this is mostly the speed in our queries. We'll talk about index-free adjacency in a little bit that gets to this. This allows us to traverse the graph in constant time, regardless of the size of the data. So the performance of our local graph traversals are not dependent on the size of our data set. We'll talk more about this later. But eBay experienced this when they used Near4J to replace MySQL for a logistics use case. And they said they found Near4J to be thousands of times faster with less code. And this is what we like to call the minutes to milliseconds performance. So oftentimes in a relational database, an application that has many, many joins, you see performance start to break down. Some of your queries can take minutes to return. And when you implement that functionality in Near4J, you see those same queries, results returned in milliseconds. I saw this at a previous company that I worked at prior to joining Near4J, where we replaced MySQL with Near4J. A dashboard that took about a minute to populate with Near4J's took something like 20 milliseconds. So this is a very common observation. The next benefit here is agility. And with agility, we're talking both about the naturally adaptive data model. So the graph data model is very easy to evolve. I like to think of data modeling with a graph as a very agile process. You sort of start with your initial take on the data model, work with some data, write some queries, see what works, and it's very easy to evolve, whereas that's certainly not the case with a relational database where we have to go through schema migrations, and it's a lot more work to update our application code. But the other piece of this is the query language that is designed for graphs. And this query language is called Cypher. Let's just briefly compare a SQL statement. This is a SQL statement that a customer sent us. And this is the same query in Cypher. So basically what they wanted to do was find someone in the organization and count the number of reports up to 3 levels deep in the organization. So it's much simpler, much more straightforward in Cypher than in SQL. And the reason for that is that Cypher is designed for connectedness, designed for graphs. And so we'll see a bit later much more about Cypher and exactly what the syntax here means. But for now, I think this is just sort of a nice intuitive way to compare SQL with Cypher. So let's talk about some common use cases for Neo4j. These are, at a high level, some of the most common use cases that we see folks using Neo4j for. It's certainly not the exclusive list, but let's dive into a few of these. The first is real-time recommendations. So if we think about modeling customers and the products that they've purchased as a graph, we're able to traverse the graph to answer questions like, what products might someone who viewed this potting soil be interested in purchasing? And Walmart uses Neo4j for exactly this use case. Another common use case is master data management. So think about, in a large organization, all of the different systems that are storing information about customers, about leads, about employees, supply chain, all of this. Well, with a graph model, it's very easy to bring in data from different systems to create your sort of customer 360 view or keep track of all of the information about different pieces of a customer throughout your organization. Cisco uses Neo4j for this purpose to build a single source of truth, and also it's at the heart of their help desk solution, so being able to bring in information about support tickets, knowledge base articles, messages from the messaging system with customers, to bring those all into one system, into Neo4j, to be able to make sense of what's going on with the help desk. Fraud detection. Fraud detection is another common use case for Neo4j, specifically in the financial services industry. Turns out that if you model credit applications as a graph, what you find is that fraud rings often share pieces of their identities across different applications for credit. So they might share an address, they might share a social security number, they might share a phone number. And with a graph, it's very easy to see these different overlapping pieces of their identities and to be able to determine which accounts might be fraudulent because they're connected to other fraudulent accounts. Graph-based search. So think of all of the metadata that's available for things like video content, articles, products, and so being able to model that metadata as a graph allows us to enhance search. It allows us to be able to put search results in the context of the user, to be able to find things that are more relevant for them. So think of on something like LinkedIn or a job search, you may start typing in someone's name, so Michael, and you don't just see random results or alphabetical results for the first Michael that matches. Instead, you see your first degree connections, your second degree connections. So this is all about showing results that are relevant to the context of the user. And Lufthansa uses Near4J for this use case to manage the digital assets for their in-flight entertainment system. Network and IT operations. So if we model a data center as a graph, we can model applications, the databases that they depend on, the server that those databases run on. This allows us to do things like dependency analysis and say, okay, if this virtual machine goes down, how many applications are impacted? Do we have a single point of failure in our current deployment structure? And HP uses Near4J to model network topology for some large telecommunication providers. And the final use case that I want to talk about is identity and access management. So really, this is thinking about what user should have access to what documents, to what assets, based on different groups that they're a member of, different roles that they have in those groups, etc. And UBS uses Near4J for identity and access management as an example. So really, as you can see, graphs are everywhere. We like to say this at Near4J, and I think it's really true. Once you start thinking in terms of graphs, you'll see use cases for graphs pretty much everywhere you look. And really, that's evident if you look at a lot of the companies across many, many different verticals that are using Near4J. You can really see that graphs really are everywhere in almost every industry. Great, so let's jump into the day in the life of a relational database developer. What are they thinking about? SQL. And they're very familiar with structures like this. So this is a table. Here we have some information about students, the country that they're from, their hair color, and the university that they went to. So we might start out modeling all of this data in a single table, but really we see that we're duplicating some information here. We're duplicating country. So what we might do is extract country out into its own table, assign it a primary key to represent each country, and then that allows us to add additional attributes for the country, so we can store the leader of the country in that table. And then when we want to reference that country from our student table, we use a foreign key that points to the primary key of the country. And this is good. We don't have duplicate data. If we want to update some information about the country, we just have to do that in one place in the country table. We might do the same thing for our university table. So create the university table, add a primary key for those, and then the university in our student table becomes a foreign key. So now, instead of having a single table, we have a data model that looks like this, where our student table has relations with a country table and our university table. So we end up writing joins if we want to do things like find all of the universities in Connecticut, the students who went there, their hair color, etc. We end up writing join like this, which may not seem too bad, but imagine if our data model becomes much more complex. We end up joining across 12 or even more tables. Think of the added complexity in our query. So now our SQL developer is thinking about joins, thinking about joins during the day at work, thinking about joins at night, keeping her up. And what's the problem here? Well, in addition to the added complexity from sort of data modeling and writing queries, there's also a performance issue here. So we have to create an index on any attribute that we're joining on. And so as the data grows, as our model becomes more complex, we see performance start to degrade. So what's the result, or what's the way to solve that? Well, we can go back to denormalizing and back to a single table, but then we have the same issues that we had before, where we're duplicating data. If we need to make an update, we have to do that in multiple places in our table. And so it's this tough balance between complexity in the data model and performance. So I like to think of these as our SQL panes. So it's actually very complex to model and store relationships in a relational database. We see performance degrade when we have many joins and increases in the size of the data. SQL queries are not fun to write when we have to write lots and lots of joins. They become very complicated and very difficult to maintain. So compare that with how we model and query data in a graph database. Relationships are a first-class citizen in a graph database. So there's a data structure that specifically takes these relationships into account. Performance of traversing a relationship is done in constant time. So our query performance does not break down as the data grows. Cypher is designed, Cypher the query language is designed for graphs, so it's very, very straightforward to write these graph traversals based on pattern matching. And because of the nature of the graph data model, evolving our data model is very straightforward. We don't have to work with schema migrations. So let's compare sort of how we model relationships in a graph database with the relational model. So here we have Andreas, who knows some of his friends in the graph model. That's represented simply by a relationship directly from Andreas to each of his friends. But as we know, in the relational model, we have to go through an intermediate join table. So we have to join person with friend in the person-friend join table. And again, this looks okay because we're just doing one join here, but imagine how this breaks down when our data becomes much, much more complex. And we'll see an example of that shortly here. Okay, so what does a graph actually look like here? Well, let's take a look at Cypher, the query language for graphs. We saw a little example of this earlier when we were comparing that long SQL statement with the much shorter Cypher. But let's take a very simple example here to start with. So here we have two people. We have Anne, we have Dan, and we want to represent that Anne loves Dan. So how would we do this in Cypher? Well, Cypher is all about pattern matching. So we simply define the pattern that we want to create. So nodes are represented by parentheses. We then add a label to the node that you can think of as sort of the class or the type of the node. Here we're going to use the label person, and then we can add properties, so key value pairs, onto the node. In this case, we're going to add a name property to each person node, one for Dan and one for Anne. And relationships are defined within brackets. And in this case, we want a loves relationship. And note here that this relationship has a direction. So we use a caret to indicate the direction of the relationship. In this example, this is a create statement. So if we ran this against Near4J, we would end up with two nodes being created, one for Dan, one for Anne, with this loves relationship connecting them. So the point here is that really Cypher is all about pattern matching, and we define these patterns using this type of ASCII art, essentially just drawing the graph that we want to define the pattern for. So as a graph, our student table might look something like this, where we have a person node with a relationship to a country, so that person lives in this country, the state is located in that country. We might have university nodes, so a person went to the university, and so on. So rather than the fairly complex foreign keys to identify relationships, we're modeling the relationships explicitly. And that SQL query we saw earlier, where we were looking for all students who live in Connecticut and what schools they went to, might look something like this in Cypher, where we're, instead of writing joins, instead we're just writing the graph patterns that we're looking for in the graph. Okay, so how do we actually use Near4J? We've sort of talked about data modeling, we've talked about the query language a little bit, but how exactly do we use Near4J? Well, there are 3 steps really here, and we're going to talk about each of these. The first is creating your model, loading your data, and then querying your data. We've talked about modeling a little bit. We'll save loading data for the end here. Let's just jump right into how we query data. So for querying data, we can use the Near4J browser. The Near4J browser is sort of a workbench for Near4J. It allows us to write Cypher queries and then visualize the results. We'll see some examples of the browser in a minute here. We also use Near4J from many different languages. So rather than just writing queries in the workbench, at the end of the day, we're building an application, and our application needs to speak to Near4J from some different language. So we have great support for lots of different language drivers in JavaScript, Java, Python, Ruby, .NET, PHP, some of the very common languages, and also we have some great community projects for drivers in languages like Haskell, Go, Elixir. So you can really use Near4J from pretty much any language, which I think is really awesome. In addition to sending Cypher queries from one of our language drivers, you can write user-defined procedures. So this is Java code that is deployed to the database and is callable from Cypher. So you can think of this as a way of extending Cypher with user-defined procedures. And again, we'll see an example of these later on. And Near4J works very well in a polyglot environment, so it's no longer the case where we're using a single database to power our application. We live in a polyglot world, so our databases are often used together to power a single application. There are tools for Near4J to work in that type of environment. So here's sort of a simple example where we've deployed a Near4J cluster. So we have 3 instances of Near4J that our application is talking to. We also might have some sync data back and forth from Near4J to other databases. And then also we may be running some internal analytics or business intelligence queries directly against Near4J in addition to our application. So this is a common architectural setup for a polyglot Near4J application. So let's talk about moving data from a relational database to Near4J. And if you think about this, there are sort of 3 approaches here when we're introducing Near4J. The first is simply migrate all of the data into Near4J, and then all queries go from your application to Near4J. Another use case would be to migrate just a subset of the data. So we take just the piece that we're interested in from our relational database, save that into Near4J, and our application knows that, okay, graph queries go to Near4J, and all their queries go to our other database. And the third option here is to duplicate a subset of our data. So we may still write all of our data to the relational database, but we're only migrating over some of that to Near4J. And so a common use case here might be if we're using a relational database for our product catalog and to keep track of user purchases, we may want to duplicate some of that data into Near4J, information about products and purchases, to be able to generate product recommendations using Near4J, while we're still using the relational database for the other more transactional piece of our data. Cool, so let's take a deep dive into how we would actually model some of this. So I'm sure most of you are familiar with ER diagrams. This is the ER diagram for the Northwind data set. This is sort of the standard example that's talked about for data modeling in relational databases. And what we're going to do today is look at how we can translate that data model to a graph model. We'll look at how we can import that into Near4J and how we can write some queries that answer some interesting questions of the data. So instead of that ER diagram that we saw, our goal is to produce a graph where the data model looks something like this. So we may have nodes for employees, we may have nodes for orders, employees sold the order includes some product, that product is in a category, and so on. And my goal is to convince you that Northwind is better as a graph. So great, so let's start with the ER diagram. So here's Northwind. How do we convert this into a graph? Well, the first thing we do is look for the foreign keys. And we're just going to cross these out because really we don't need these foreign keys in the graph model. But we do need names on our relationships. So we will add some names for our relationships. The next thing we'll do is identify all of the join tables. So here we have an order details join table, and we have this employee territories join table that's joining employees and territories together. And simple join tables just become relationships. So an employee represents some territory, and our join tables with attributes become relationships as well, but we need to store the properties on those relationships. So here, orders will include some product, but we need to store the unit price, quantity, and discount as properties on this includes relationship. And we end up with something like this. So let's see how we would query a subset of Northwind. So if we had this piece of Northwind as a graph, let's see how we would write some queries to answer some interesting questions. So here's the graph model that we're going to be working with. We have employees. Employees have sold some order. That order includes a product. That product is in a category, and we know the supplier that supplies the product. And these are all represented by nodes and relationships in our graph model. So how do we query this? Let's do this using OpenCypher. So I say OpenCypher because Cypher was open sourced last year, to the Open Cypher project, and so it's really becoming sort of the query language for graphs, not just on Near4J, but also implemented by other vendors as well. So let's look back to how we write a Cypher query, and remember that it's all about pattern matching here. So the first query we're going to write is sort of a who reports to whom query. So here we have employee nodes, nodes with the employee label that have a first name property, and these employee nodes are connected by a reports to relationship. So just remember here how we're defining patterns, both labels, properties, nodes, and relationships with this sort of ASCII art in Cypher. So who do people report to? So we don't have to specify property values. In this case, we're going to use a match clause. You can think of match as similar to a select statement in SQL. So we say match, we then define the pattern that we want to match on. So here we want to match on every employee that reports to another employee and return everything. So return the subgraph that matches that pattern. And this is what we end up with. We can see that Stephen reports to Andrew. We can see that lots of other people report to Andrew as well. This gives us sort of the hierarchy of the employee reports to piece of the organization. Now this is modeled as a graph. That's how we would see it if we ran that in the Near4J browser. But we can also return the results in tabular form. So before we were just returning using the asterisk, and that returned the entire subgraph, but we can also specify what pieces or what values we want to return. So you can see in our match state, in our match clause, before the employee label, we have an E, and then on the other end we have a sub, so we have an employee and then a subordinate. And the E and the sub, those are aliases. So each path that matches that pattern, the nodes are bound to those aliases, and we can then refer to them later on in the query. In this case, we're just going to use them in the return clause. So we're going to get the employee ID and the first name of the manager, and the employee ID and the first name of the subordinate, and return those as well. And because we're just returning strings here, the results will be displayed in a tabular format if we were to run these in the browser rather than the graph format. Now here we'll use a where clause to find Robert. So here we're saying find who Robert reports to. And we can see that Robert reports to Stephen. Now, one thing that's really important about Cypher is that we can define variable length paths. So here we're using an asterisk in the reports to relationship. And what this says is follow this pattern. So employee reports to employee, but follow this a unlimited number of hops. So follow all paths that match this pattern using multiple reports to relationships. So really what we'll do here is we'll start at Robert and we'll see the entire chain. So we'll see that Robert reports to Stephen, and then that Stephen reports to Andrew. So let's find out who is the big boss here. So let's find an employee that does not have a reports to, an outgoing reports to relationship. So remember that relationships here are directed. So we're saying match on an employee where we do not have this pattern and return his first name as the big boss. And if we remember the results from our previous query, we see that Andrew is the big boss because he does not report to anyone. We can define much more complex patterns. We can also use aggregation functions for things like reporting. So here we're looking at product cross-selling. So for this product, chocolate, let's find the employees that have sold orders that include it. And then let's look at other products that those employees who are selling chocolate are also selling. So much more complex query than what we saw before. And here we can see that Margaret is most commonly selling some sort of gnocchi with chocolate, and that's the most common product cross-selling with chocolate. Cool. Well, for more hands-on introduction to Cypher, we have a great online training with these interactive widgets that walk you through learning Cypher and will challenge you and test you as you're learning Cypher. So if you're looking to learn more about Cypher, I'd strongly recommend the online training. It's a great way to get started. So the results that we saw in those screenshots, those all came from the Neo4j browser. But like I said, oftentimes we're building an application. We're not just running queries in a workbench. So how does it work when it actually comes time to build an application? Visualization is often an important piece of this. There's a application running on network.graphdemos.com that allows you to pull in your own Twitter data in real time, use that in Neo4j. This is an example of visualizing some of that data from my colleague Ryan's Twitter feed. So visualization is often a key component of it, but we can also use Neo4j to power more traditional type of applications. Here's a super simple reporting application that just queries similar to the queries that we saw before, who reports to who, and variable length paths of reporting and so on to show us in a tabular form the structure of the organization. So let's look at the code for how we might power this simple application. So this is some Python code. The first piece here is we're using Py2Neo, which is one of the Python drivers for Neo4j, to connect to a Neo4j instance. We just specify the host and port that Neo4j is running on, as well as the password. That connects us to a Neo4j instance. The next piece here is we're passing as a string our Cypher query. This is basically just what we saw before, finding employees who report to other employees, and then collecting their names so that we can return those names to populate each list item in an unordered list. So we have the results after calling graph.cypher.execute, and we just need to iterate through our results and we're creating some simple HTML here using the values that came back to populate our list in HTML. So that's just a super simple example of how we might use Neo4j from Python to build some HTML to power a simple application. Great, so that covers the querying our data piece, but we skipped an important part, and that's loading our data. So let's see how we can actually load data into Neo4j. And we'll assume we're going to be loading data from a relational database or data that we already have. And one of the most common ways to do that is using CSV, comma separated values format, as an intermediate step. So most databases have some capability for exporting to CSV. And for this reason, a lot of the tooling for import in Neo4j is built around CSV as an intermediate format. So if we take the Northwind database and we dump each table to a CSV file, we'd end up with a series of CSV files that look something like this. So our CSV files have headers and then comma separated values. Here we're looking at orders. So we have an order ID, customer ID, employee ID. These are the foreign keys, right? So sort of what we would expect. Now there are three basic steps when we're importing our data here. The first is to import our nodes. Next is to create indexes. We'll talk a bit more about indexes in Near4J. And then to create our relationships. So let's start with importing our nodes. So in this case, we're using functionality in Cypher called load CSV. So load CSV you can think of as kind of a ETL tooling built into the query language that allows us to load CSV files from the file system or from some remote URL. And it allows us to iterate through each row of the CSV file and then using Cypher define and create the graph with the results of those values. So here in this first statement, we're loading the customer's CSV file, and then we're creating a customer node for each row in the CSV file, storing the company name, customer ID, their fax number, and their phone number as properties. And we do this for products as well. And then for suppliers and employees, again, just iterating through each row of the CSV and creating a node for each row. Now, note here that we're using, at the beginning of our statement, using periodic commit. Now, this allows us to bypass the transactional nature of Near4J when we're importing large amounts of data to avoid building up the transaction into memory. So when you see using periodic commit before a load CSV, that's the reason, purely for performance. Now, next step is to create our indexes. So indexes in Near4J are used a little bit differently from indexes in a relational database. In a relational database, typically we're creating indexes to facilitate joins, so values that we're going to be joining on. In Near4J, typically we use indexes to do an initial lookup. So let's say we're generating product recommendations for some user. We might look up that user by name or by ID, but then we traverse out to find their orders and the products that they've purchased. We don't use any indexes for that traversal. So really what you want to do is create indexes on things that you're going to be doing just that initial lookup. So here we're going to be looking up products by name and by ID, so we create indexes on those. But we're not using indexes for any of our actual graph traversals. So now that we've created our nodes and relationships, we need to create we've created our nodes and indexes. Now we need to create our relationships. And we do this by loading any CSV files that we know are going to have foreign keys. So we know that the orders table does. So we load the orders table, or the CSV from the orders table. We're matching on the order ID. So for each row, matching on the order ID, matching on the customer ID, and then we use this merge statement to create a relationship from the customer to the order. And we do this for products as well that have the foreign keys for supplier and product. We do this for orders that include some product. And now remember on the includes that was an attributed join table. And so we need to be sure to store the unit price and quantity on the relationship here as we're creating that. And we'll do the same for our employees and again for product categories. And that allows us to import the Northwind graph. It's important to note that load CSV works pretty well for CSV files of up to a few million rows. If you have an initial import larger than that, there is a command line Near4J import tool that can load much faster. It bypasses the transactional nature of Near4J. So again, this is another tool that's available for large initial imports. So in addition to load CSV, we can also connect to relational databases from Near4J using JDBC. Specifically in this apoc.load JDBC user-defined procedure. So we mentioned user-defined procedures just very briefly at the beginning. We said they were Java code that's deployed to the database and then callable from Cypher. Folks at Near4J and community members have been working on what we're calling awesome procedures for Near4J, or the APOC library that contains lots and lots of different procedures that can be used. These are some of the built-in procedures that are available without APOC, so things like finding out all of the labels in the database, but the things in APOC allow you to do things like connect to other relational databases, to load data from the web. So here we're just loading JSON from some web URL. There are things for full text indexes, lots and lots of things in there. Don't have time to talk about them all, but the one I do want to talk about is specifically APOC load JDBC. So let's see how this would work to import a piece of Northwind. So let's say we wanted to import just orders, products, and customers. We want to end up with a graph model that looks like this. How would we do this using JDBC? Well, the first thing we do is register the driver. So we're using MySQL. We're just registering the MySQL JDBC driver. Actually, I have this running locally, so let's go ahead and do this. So I have MySQL running here with Northwind. So here's our Northwind database. Also have Near4J running locally. Let's delete everything. Sure, there's nothing in there. Great. Oops. Match A. Okay, so nothing in there. So the first thing we want to do is register our JDBC driver. So we do that, and now we want to create product nodes. And so you can see this is very, very similar to how we would do this with load CSV, but instead of load CSV, we're calling this APOC load JDBC. We're giving it this JDBC connection string to connect to MySQL running locally on my machine, and we can specify the table, or we can specify some SQL statement here. So if we just wanted to do iterative updates, we could grab every update from a certain time or whatever. In this case, we're going to get every row from the product table. So we run that. We've created our product nodes. We're going to do the same here for order nodes. Now let's create this contains relationship. So orders contain some product. So we're going to match on the product ID and the order ID from this order details join table and create this relationship. Let's create our customer nodes and this placed relationship so that we can see orders that customers have placed. So now that we have this, we can generate some product recommendations. So one way to generate personalized recommendations is to look at products that a user have purchased, find other users that have purchased that same product, figure out what those users have purchased, and recommend those to the initial user. And so here we're doing exactly that for some user named Roland Mendel. We're looking at all of the products he's purchased. Note we have to go through the order node to get to those, and then generate recommendations. We're using the number of paths that we've found as a weight. And so here we can see Gorgonzola Tolino is the #1 product recommendation for Roland. Okay, so that was just meant as a quick example to show how to import data from MySQL into Near4J using the JDBC procedure. All those queries are in the slides here for reference, as well as just a little bit about generating recommendations. The next tool I want to talk about is the Near4J JDBC driver. This allows you to use lots of ETL tools such as Talend to import data from a relational database into Near4J using Talend just as you would for any of their other ETL pipelines. And this is exactly how the ICIJ imported data from the Panama Papers leak from a relational database into Near4J, was using Talend. And the JDBC driver works with lots and lots of BI tools and ETL tools. There's a great blog post talking about the JDBC driver. So if you're interested in that, I would encourage you to check that out as a resource. So just to wrap up here, I just want to mention a few resources that are out there for technical getting started resources, sample code, use cases, and some getting started guides. Near4j.com/developer is a great start. You can also download the O'Reilly Graph Databases book for free at graphdatabases.com. There's a lot in here on data modeling, learning Cypher, different use cases, and this is recently updated for the 2nd edition. Also, it's important to point out that Near4j is an open source database, so you can download it right now and get started. If you do that, there are these great browser guides that are built in. So if you want to do some more hands-on things with Northwind as a graph, you just type :play Northwind graph in the Near4j browser. Once you have it running and you have this great guided experience to go through Near4j. Let's try this here. Play Northwind graph. And we have this guide that pops up, shows us how to load data from Northwind. We just click on these queries to load them into the editor. So just want to mention that as a resource. And that's all I have. So thank you very much to everyone joining today.